pleasure to start it with a talk by Professor Ashoke Sen, who will explain in half an hour what is string field theory. Please.
Okay, thank you. Well, okay, so I don't quite intend to explain string field theory as such, but I'll try to explain how string field theory is used to analyze unitarity and analyticity in string theory. So let me give a brief plan. So I'll begin with an introduction to string field theory. In fact, this will be very short. And then I'll discuss these two aspects, the proof of unitarity as well as proof of analyticity using string field theory. And in that process, I'll also explain why string field theory is necessary and the worldsheet method is not sufficient to analyze these two cases. And the talk will be based on essentially these two papers. Okay, this is on unitarity and this is on analyticity. So let me begin with an introduction to string field theory. Now we know that amplitudes in string perturbation theory are usually expressed as certain integrals over the string worldsheet. But these integrals often run into divergences. And the simplest example of this is the Veneziano amplitude, which is the first amplitude that was ever written down in string theory. And from the worldsheet perspective, it's given by the simple integral. And P1, P2, P3, and P4 are the external momenta, okay, all counted as ingoing. Now, as we see from here that this integral diverges whenever 2P1.P2 is less than or equal to -1, or 2P2.P3 is less than or equal to -1. Okay, so this corresponds to large S, and this corresponds to large T. And the conventional viewpoint that one takes here is that we define the amplitude for in the regimes where they are well defined, namely for 2P1.P2 larger than -1 and 2P2.P3 larger than -1, and then analytically continue to other kinematic regions where it's divergent. Now, as I'll discuss in the next slide, string field theory provides a different but an equivalent viewpoint to these divergences. So what is string field theory? So string field theory is a regular quantum field theory with infinite number of fields. And it's designed so that the Feynman diagrams of the theory formally reproduce the amplitudes based on the worldsheet formalism. And it's important to note this word formally, and I'll explain in what sense it is formal. But in string field theory, you also have a very clear physical interpretation of the divergences that you normally encounter in the worldsheet description. So for this, let's consider the Swinger parameterization of a propagator in quantum field theory. So if you encounter a propagator like k square plus m square inverse, the Swinger parameterization expresses it as an integral of this kind. Or sometimes you can also express this as an integral over this variable q, which is e to the minus s. Now you can easily see that this equality is an identity as long as k square plus m square is positive. But when k square plus m square is negative, the left-hand side remains finite, but the right-hand side diverges. And when we translate the string field theory Feynman diagrams to the worldsheet language, okay, and this is possible because of this, because the string field theory is designed to formally reproduce the worldsheet formalism. But during this translation, we see that the q's become the variables over which we integrate. So for example, this variable y that we encountered here is related to q with some appropriate functional relationship. And all the divergences that we encountered in worldsheet formalism can be traced in string field theory to the regions where one or more of the q's vanish, okay, where a q corresponds to this parameter associated with the corresponding propagator. So the lesson from this is that whenever in a string field theory Feynman diagram, the internal propagator has k square plus m square negative, then the corresponding worldsheet expression diverges, and we need to define it by analytic continuation. But we also know that in a quantum field theory, the imaginary parts of the amplitudes arise precisely from this region, okay, where one or more propagators, internal propagators, go to above the threshold. Okay, so k square plus m square, my notation is it's mostly plus signature. So k square plus m square less than 0 means that we are gone above the threshold of production of the particle of mass m, and that's where the interesting physics occurs. The imaginary parts come from there, and the issues of unitarity and analyticity all are related to the behavior of the theory in this region. So because of this, we see that the string worldsheet formalism is not very convenient to study the properties involving unitarity and analyticity, because whenever this is less than 0, the worldsheet expression diverges. And because of this, the unitarity and analyticity properties of string amplitudes are best studied using string field theory rather than using the worldsheet formalism. So now let me give a brief introduction to string field theory. So in particular, I'll focus on superstring field theory where there are no tachyons, because if there are tachyons, then the theory is inconsistent and it's not really clear how to define loop amplitudes. But superstring field theory has infinite number of fields, as I have already said. And the gauge fixed action has this structure. So it has a kinetic term. Okay, kinetic term, in fact, is quite simple. Okay. It's quadratic in momentum. Okay, so no higher derivatives in the kinetic term. Okay. And in fact, in the appropriate gauge, the kinetic term is diagonal and it takes the form of k square plus m alpha squared times delta alpha beta. Okay. So it's a diagonal kinetic term. It's easy to construct the propagators from here. So this is the analog of the Feynman gauge in a gauge theory. Okay, the gauge in which this happens is what is called the Siegel gauge in the context of string field theory. Where string field theory differs from ordinary quantum field theory is in the structure of the interaction terms. So these interaction terms in the momentum space turn out to have exponential suppression factors of this form, where A is a positive constant, and in fact we can take A to be as large as you want by an appropriate nonlinear field definition. In the language of string field theory, this is what is commonly known as adding stubs. Okay. But the important point is that you have this suppression factor, okay, and this acts as a suppression factor whenever the spatial components of the momentum goes plus minus infinity, or the time components of the momentum go to plus minus I infinity, okay, because of this minus sign over here. And this is going to be important in what follows. So this implies that if we consider an interaction vortex like this, these vortices will be accompanied by a suppression factor of this kind. And this means that the momentum integrals, first of all, are ultraviolet finite, okay, with appropriate prescription that I'm going to describe in the next slide. But this also has another consequence, okay, namely that even though string field theory contains infinite number of fields, and hence in the intermediate state, there are infinite number of fields that are propagating, so you have infinite sum. Okay. The number of states at mass level ms grows as exponential of ms. Okay. So that growth is compensated by this exponential suppression at the vortex, because it goes as e to the minus a times ms squared, okay, whereas the number of states grows as exponential some constant times ms. Okay. So this makes the sum of our intermediate states converge, okay, and at the same time, it makes the momentum integrals converge if we choose the integration contour appropriately. So here again, the factor in the vortex. Okay, this of course is one of the factors. It also has other factors which are polynomial in momentum, which are much more complicated to write down. But from this vortex, it's clear that the integration over the ki's will converge for large real ki, but the integration over the ki zeros will converge for large imaginary ki zero. So each Feynman diagram is manifestly ultraviolet finite as long as the ends of the energy integration contours are pinned at plus minus I infinity, and the ends of the spatial components of momentum integration contours are pinned at plus minus infinity. Now it turns out that at least for real external momentum, okay, or for a class of external momentum, we can always take the spatial components of loop momentum along the real axis, but the integration over the loop energies have to be treated more carefully. Okay, and this is what I'm going to describe in the next slide or next two slides. So this is what I've already said, that the ends of the loop energy integrals have to be pinned at plus minus I infinity. Okay, you can rotate it a little bit, but not too much. Okay, in particular, you cannot do weak rotation of the contour, where you make it lie along the real axis. But for a generic external momentum, in the interior, the contour has to be deformed away from the imaginary axis to avoid poles from the propagators. Okay. And how we do that, I'll describe in the next slide. Okay, but this is the general feature of the integration contours in the loop energy space. Okay, in the spatial components, we take the momentum integration contours on the real axis. So we are now going to describe in detail how to choose the loop energy integration contour. So here is a general procedure. So we multiply all external energies by a complex number. Now for U equal to I, all the external energies are imaginary. And we can take all the loop energy contours to lie along the imaginary axis, okay, because then the ends are moving at plus minus I infinity anyway. And this doesn't encounter any singularity because this makes all the internal loop energies strictly imaginary and all the internal spatial components of loop momentum strictly real. So all propagators are perfectly real and finite. So there is no divergence. So at least for U equal to I, it's clear that there is no divergence. And now the prescription that one chooses is to deform U to 1 along the first quadrant. And during this deformation, if some pole of a propagator approaches the loop energy integration contours, then you deform the contours away from the poles, but the ends of the loop energy integration contours have to be fixed at plus minus I infinity. And one of the results that we found during our proof of unitarity is that such deformations are always possible as long as U lies in the first quadrant, which means that if you deform the contours this way, then the loop energy contours do not get pinched by poles from two sides. But I should also add here that if we had tried to deform each energy independently in the complex plane, then this proof doesn't hold anymore, and you could encounter pinch singularities along the way. Okay, so it's important that we scale each energy by the same complex number U, and then deform the single complex number from the imaginary axis to the real axis. Now, normally in the weak rotation, as you do this, you will also rotate the integration contour by the same multiplicative factor U. Okay, so the integration contours rotates in the complex energy plane as the external energies rotate. But this you cannot do here. As I said, the ends have to be fixed at plus minus I infinity. Okay. So now let me state the results on unitarity. Okay, what we get from this analysis. So what we get from this analysis is that the amplitudes computed this way satisfy Katkowski cutting rules. Namely, that it satisfies the appropriate relation between T minus T dagger and T dagger T. And it's proved by using contour deformation in complex loop energy plane. Okay, the proof is a little technical and complicated, but this is essentially what we proved. And I should also add that normally in local quantum field theories, the easiest way to prove cutting rules is using the largest time equation. That unfortunately is not available here because that is a property of the Green's function in position space. And because of this non-locality of the vortices, it's not clear how to construct the corresponding Green's functions in string field theory in position space. Okay, so that's why you have to work directly in the momentum space in the proof of unitarity. Now, of course, this is only a step towards proof, the proof of unitarity, but not a complete proof, because when you write T dagger T in this form, okay, by as a sum of complete, by inserting a complete set of states, okay, in the Siegel gauge, the sum over intermediate states runs over all states in the Siegel gauge, okay, which means that it includes physical states, but also it also includes unphysical states. And the desired result, of course, is only physical states should contribute to the sum. Only then we will say that we have proved unitarity. And this can also be shown using quantum order entities in superstring field theory. Okay, here the proof is a little different because we do the Batalin-Minkowski quantization. But as in the case of normal gauge theories, it requires cancellation between the matter and the ghost loops. Okay, but this can also be proved diagrammatically that all the unphysical states contribution goes away at the end. Okay. And this essentially proves unitarity to all orders in string perturbation theory. So let me add that the proof of unitarity takes into account the possibility that mass and wave function can get normalized. Okay, here of course everything is finite normalization because there's no ultraviolet divergence. At tree level, there is a lot of degeneracy. They are lifted typically by loop corrections. Okay, that is taken into account. Then the fact that some, or in fact most of the string states become unstable under quantum corrections. Okay, that's also taken into account. So in the full unitarity relation, the cut actually runs over only the stable states. It also takes into account the possible shift in the vacuum due to quantum effects. Sometimes what may happen is that the quantum corrections make the perturbative vacuum unstable, but there is a nearby vacuum which is stable, and you can quantize the theory around the nearby vacuum. The proof of unitarity goes through even for those vacuum. What has not been done explicitly, but I don't anticipate any problem, is that it does not take into account the infrared divergences from soft particles arising in d less than or equal to 4. Okay, so the proof is complete, of course, for in 5 and higher dimension, but we know that in 4 or less dimensions, there are infrared divergences, and you have to define appropriate quantities by summing over soft emissions. And one expects that that also goes through exactly as in normal gauge theories, because after all, the low energy behavior is like that of a gauge theory, right? String theory differs from gauge theory only at high energies, but this has not been done explicitly. So let me now turn to the proof of analyticity. So let me state the problem first. So for this, let's consider a scattering amplitude of n particles, and we'll take the all momentum to be ingoing. Okay, so the outgoing momentum will be represented by negative of the pi's. So some of the pi zeros are positive; they represent ingoing states, and the pi zeros which are negative represent the outgoing states. Okay, they satisfy on-shell condition like this. Okay, so this I have already said. The metric convention is mostly plus, so this is our ps square. Okay. And we define the usual Mandelstam variables SAB as minus PA plus PB square as usual. And the question that one asks in the study of analyticity is in which domain of the complex space of Mandelstam variables is the scattering amplitude analytic. And this is a useful starting point for studying many other properties like the crossing symmetry, dispersion relations, and so on. And let me also add that this statement is a statement about the on-shell amplitudes. We are really talking about the S matrix. And you are asking that in what domain in the Mandelstam variables, the S matrix is analytic. So to study this in string theory, let's first ask how is it studied in local quantum field theory. So for this, let's consider the off-shell amplitude of off-shell amputated Green's function, which means that the external propagators are removed. Okay, we call this G P on to Pn. And up to the some external wave function deformation factors, the S matrix is essentially this amputated Green's function evaluated on shell. Okay, so take the amputated Green's function and set PS square equal to minus MS square. Okay. And here you have dropped the Lorentz indices that the S matrix might carry, but they are present implicitly and they do not affect any of the analysis that I'm going to describe. So now let's define this quantity capital P alpha. So what is this index alpha? So A alpha represents any subset of the indices 1 to n. So take any subset of the momentum, and their sum is what I'm calling P alpha. Okay, and this way there are many such P alphas. There are in fact 2 to the n P alphas. And of course, not all are independent, like half of them are minus the other half because of the momentum conservation. But let's take the collection of all these P alphas. Now, if we have a local quantum field theory, then it was shown, in fact, long time ago, that just based on the locality of the position space Green's function, one can show that this Green's function is analytic in the following domain. It's analytic if all the imaginary P alpha, it's analytic if there are two cases. If imaginary P alpha is not 0, then imaginary P alpha must be time-like. Then it is analytic. If imaginary P alpha happens to be 0, then P alpha must be such that it's below the threshold of production of multi-particle states. which basically means that the momentum P alpha cannot split up into a set of momenta which are all on shell. So this domain is what is normally called the primitive domain of analyticity, and I'll denote this by D. And as I said, based on the locality of the position space Green's function, one can show that this Green's function is analytic in the primitive domain of analyticity. Now, simple kinematics, okay, just momentum conservation and the on-shell condition shows that this domain D has no intersection with the subspace in which the external states are on shell. Which means that if you put this condition, P square plus M square equal to 0, then there is no PA that satisfies this, and at the same time, it satisfies the condition that it lies inside D. So the apparent conclusion from here will be that the analyticity of G in the primitive domain of analyticity is a useless fact because it's useless for exploring analyticity properties of the S matrix. Because here we always want on-shell external states. Okay, however, it turns out that there is a way out. And this way out relies on some property of the function of many complex variables. So let's suppose that you have a function of n complex variables, multiple complex variables. And suppose you know that it's analytic in some domain D, okay, just like in the previous case, okay, that this function is known to be analytic in some domain D. Then one can show that without knowing anything else about the function, but just the fact that it's analytic inside the domain D, we can often prove that the function is analytic in an extended domain, which I can call W. This is sometimes called the envelope of holomorphy. Okay. Holomorphy in D implies automatically that the function must be holomorphic in W. So let me emphasize again that this domain W depends only on the original domain D. That is analytic in domain D can be proven to be analytic in the domain W. Okay. And there is an explicit algorithm for constructing W from D, which I'm not going to describe, but it's good enough to know that there is such a W. Now, this is different for function of one complex variable. Because if you have one complex variable, then given any connected domain R in the complex plane, one can always find a function f of z that is which is analytic in R and non-analytic on the boundary of R. So knowing that fact that the f is analytic inside the domain R doesn't allow you to extend it outside R. Okay, in some cases you may be able to extend it, but it will not hold in general for all functions f of z, which is analytic in R. So here is an example. Suppose we have a function of two complex variables, and it's known to be analytic in disk times annulus. Okay, so unit disk times part of a unit disk, which is an annulus, and also on annulus times disk. Okay, that means disk of in the Z1 plane times the annulus in the Z2 plane plus annulus in the Z1 plane and disk in the Z2 plane. Then we can prove that f Z1 Z2 is analytic in disk times disk, okay, which is a bigger space than this. Okay, because certainly disk times annulus plus annulus times disk leaves out some regions, okay, which disk times disk includes. Okay, where the point Z1 is inside the annulus and Z2 is also inside the annulus. Or Z1 is outside the annulus and Z2 is outside the annulus. So the proof of this, in fact, is elementary. I'll not give this, but it's elementary using Cauchy's integration formula. But it can explicitly construct an analytic function which can be extended to disk times disk. So using this kind of argument, one can in fact extend the domain of analyticity of the G to beyond the primitive domain. So just by knowing that G is analytic in the primitive domain of analyticity, we can find a bigger domain. And the extended domain W indeed do include points that satisfy on-shell condition. And this can be used to prove interesting results. And so far it has been applied mainly to 2-2 scattering. And this can be used to prove interesting results about 2-2 scattering. For example, one can prove crossing symmetry, namely existence of an analytic continuation that relates A plus B going to C plus D to A plus C bar going to B bar plus D. Okay, this is an old work by Ross, Epstein, Glaser. And similarly, analyticity of the elastic forward scattering amplitude in the complex S plane and so on. So what about in superstring theory? The string theory seemingly has non-local interactions. And then one can ask, is there any signature of this in the S matrix? Namely, do the amplitudes in string theory enjoy the same analyticity properties as those of quantum field theory? Or one can see some difference because of this non-locality. Now, you notice that because string theory is non-local, you cannot apply the starting point that we had, namely that the G is analytic in the primitive domain, because this proof in a local quantum field theory relied on some properties of the position space Green's function, which are not available in string theory. So to follow the same approach as in quantum field theory, we first of all need off-shell Green's function. This, of course, we can do by using superstring field theory. And so the goal will be to prove the analyticity of G in the primitive domain D as in quantum field theory. And if we can prove this, then this will automatically imply crossing symmetry and other useful properties of one-shell amplitudes. However, in string field theory, the starting point is missing, namely the usual proof that for the analyticity of G in the primitive domain is missing because you don't have position space Green's function. So the strategy that we followed here is to basically try to prove analyticity in D directly in the momentum space using Feynman diagrams. And that's basically what we did. We carried out appropriate deformations and tried to prove that the contour is never pinched as long as you are inside the domain of the primitive domain of analyticity. Now here, let me again mention some infrared issues. That the analyticity properties in quantum field theory that I mentioned have been derived assuming that there are no massless states. Because once there are massless states, there are additional problems. And these problems are common to both quantum field theory as well as in string theory. So since our goal is to examine if string theory and local quantum field theory differ in their analytic properties, we study analyticity of string amplitudes after removing the contribution from massless fields. So basically, we take the string field theory Feynman diagrams and just remove the contribution from all internal massless fields, and then ask, is the resulting amplitude analytic? Because now it's on the same footing as in normal quantum field theory, even though the method that you have to use is different. And the idea is that any additional non-analyticity due to massless fields affects string theory and quantum field theory exactly in the same way. So what we have been able to prove is a limited version of the result. And this limited version corresponds to when imaginary PAs lie in a two-dimensional Lorentzian plane. So we haven't been able to prove for arbitrary imaginary PA lying in the primitive domain. But when imaginary PA lies inside the two-dimensional Lorentzian plane, we have proved this. And the strategy essentially was to find a path inside D prime that connects the origin to a point in D prime, and then show that as we reform the external momenta along this path, the loop momentum integration contours can be deformed to avoid singularities. Basically, you have to make sure that the momentum integration contours are never pinched, that you never encounter a situation where you cannot deform the loop momentum integration contour away from the singularity. Now, this may look like a restriction, but fortunately, analyticity in D prime is sufficient to prove all the known analytic properties of S matrix that has been proven through local quantum field theory. Like, for example, the crossing symmetry that I mentioned, or the analyticity on the forward scattering amplitude. Those all essentially use the analyticity inside D prime, namely inside this two-dimensional plane. The full analyticity in D has never been used to get an interesting property of the S matrix so far. But I should also add that for 4-point function, this proof has been extended to the full momentum space by these people. Okay, so this is more or less the end of my talk. I'll just end with some final remarks. And that is the following. That we saw that the Feynman diagrams, using string field theory Feynman diagrams, so one can get handle on the unitarity and analyticity properties of string theory. So that sounds good. But I should also add that Feynman diagrams are not the complete story in string theory, because if you really rely on the individual Feynman diagrams, they have extremely bad high energy behavior for Lorentzian momentum. For the same reason that it's ultraviolet finite, right? We saw that this exponential factor, it suppresses for Euclidean momentum, but it's, of course, it blows up exponentially as energy squared as you go in the Lorentzian direction, as you go to infinity in the Lorentzian direction. Okay, that's what I've said here. Now, this of course is bad news because this means that you cannot, I mean, if you have a generic non-local theory like this, you cannot apply dispersion relations. Now, in string theory, of course, there are magical cancellations because you know that string theory has good high energy behavior, string amplitudes. And this happens because of cancellation between different Feynman diagrams. And eventually it restores the good high energy behavior. But you really need the magic of string theory for this to happen. And this will certainly not be true in a generic non-local field theory of this type. Okay, if you just had taken exponential suppressed vortices, interaction vortices of the kind that I described and tried to define a quantum theory, okay, it will have unitarity and analyticity properties, all right, but its high energy behavior will be extremely bad. So I think with that I'll stop. Thank you.
Okay, thank you very much. So we are now having some time for questions, and if I'm correct, the first appeared in chat from Luca. So Luca, please unmute yourself. And
okay. Thank you very much for this nice talk. So actually, my question was related to this last slide. So yeah, you partially answered basically. So yeah, my worries was about this time-like exchange divergences that you have in the vertex. Okay. But as you said, in string theory, there is some cancellation. But for instance, just to understand how this cancellation happens, if we just take the cubic vertex for string field theory, we will have some kind of exponential of minus p squared phi cube, for, I mean, some field cube, okay?
Yes.
But in one of your paper, I read, for instance, that this divergence in the time-like direction will be cancelled by the quartic vertex, okay?
Yes.
So it's not clear to me what kind of quartic vertex should we write down to cancel this divergence in some amplitude, for instance. So which is the expression?
Okay. It will automatically give the quartic vortex, right? And I mean, I think if you try to see this in string field theory, it will be very complicated because the quartic vortex also has very complicated dependence on momentum, the external momentum. So if k1 dot k2 square, if S, for example, blows up, then it will have exponential growth in the Lorentzian direction, right? And that will cancel the exponential growth in the S channel diagram, for example, that you are mentioning. But the easiest to see this is by going back to the worldsheet formalism, because after all, you are analyzing on-cell S matrix, right? So for the worldsheet formalism will be good enough, right? And there you can use this Gross-Mende kind of analysis that they did using the worldsheet, right? And try to use saddle bond. And there you can clearly see that the divergences cancel and you get a nice answer as in the large S and large T limit.
But in the case of string field theory, I mean, is you're just trusting that the same should happen as in the worldsheet analysis, or there is some explicit computation where the quartic vertex has been really shown that cancel the cubic one?
Well, what has been shown is that there is an explicit quartic vortex, and when you add to the cubic one, you get the usual worldsheet amplitudes.
Okay,
but we haven't separately calculated the two and then seen the cancellation, although it should be possible.
Okay.
But one can show that the sum of the two gives you the worldsheet answer for the S matrix.
No, that's I agree. It's just that I never seen the explicit computation in string field theory.
Yeah, I don't think people have actually studied the high energy behavior of individual Feynman diagrams.
It would be nice to see because
I agree. Yeah, to just see how the cancellation works.
Yeah, because it seems to be a kind of incomplete, because it's difficult. I'm not. I don't know anything about string field theory. I just know this fact of the exponentials behavior. Okay, so it would be nice to really see an expression for the quartic vertex and how it cancels. Yeah.
So, let us try to move to another question because there are many. So it was one question from Anish. Anish, please, can mute yourself. You had a question in the chat.
So yes, so I have a couple of questions. So my first was, can you explain kindly explain a bit more when you said that there has been possible shift in the vacuum due to quantum effects has also been taken into account in your study? So I didn't understand that part. Can you explain?
Yeah. So the point is, sometimes what happens is maybe I can go to the. Let me see if I can. Yeah, that you may, what sometimes happens is that you have say some potential which has like this, which is like this. Sorry, it's all. Okay, there is a flat potential, okay, at the tree level, okay? And quantum corrections produces a potential like this.
Okay.
Okay, so quantum correction shifts the vacuum. And now the point is that, of course, the original vacuum and the worldsheet formalism tells you how to do this computation around this vacuum. In string field theory, because you have a second quantized formulation, you can always shift fields and expand around the new vacuum and do the analysis. And the proof of unitarity goes through even when you are expanding around this new vacuum. Okay, so this is the vacuum that we generate because of the quantum correction. So one loop quantum correction can shift the vacuum from the origin to a point like this.
I see. Thank you. And another curiosity is that so in your studies that the fact that the scattering amplitude are growing in the Minkowski, or they're softened in the Euclidean. So and the particular contour you're choosing and doing the calculation in string field theory, because I do not know string field theory. That is where my next question. So does supersymmetry plays a role here, or is it just a property of the Feynman diagrams and the Euclidean and
yeah, I think this is the analog of the weak rotation, right? See, normally in the weak rotation, you first define the amplitudes for imaginary energies and real momentum, right? Where everything is perfectly finite. There's no pole in the propagator or anything, right? In the Euclidean Green's function, and then you analytically continue to the Minkowski, to the Lorentz signature. Right? It's exactly analogous to that. Except that normally in weak rotation, what we will do is the following: that suppose you have a integration contour, this is imaginary k0, and this is real k0. You introduce this parameter u, right, which you can take, for example, e to the I theta, right? And you are going from theta equal to pi by 2 to 1, right, to go like this. So normally you put as you deform the external energies, okay, like this. You also rotate the contour, right? You start from the imaginary contour and then you keep rotating the contour by the same phase, and that's the weak rotation. At the end, by the time u has become real, your contour has come down to along the real axis, except for this I epsilon prescription. Okay, so this is what you cannot do. This is different in string field theory, because this kind of contour is not going to be finite, right? This is going to diverge at it. So what you do is that your starting point is the same. Your integration contour is along the imaginary axis. You start from here, okay? And then as you deform, that imagine that some, okay, so let's do this. Let's suppose your integration contour was like this and some pole comes in. As you are deforming the external energies, some pole can come in and close to the contour, right? Okay? That means that now if the pole hits the contour, you have a singularity. But you just deform the contour like this, okay, to go away from the pole. And this, the important point is to prove that this can be done without having a situation like this, right? If you had a situation like this, for example, when there are two poles on opposite sides, then you cannot deform the contour, right? If the poles are coming together. So this is what is called a pinch. And you have to make sure that the pinch doesn't happen. And as I said, as long as u lies in the first quadrant, one can show that the pinch doesn't happen. The final contour is not like this. Okay, so this is not the kind of contour you choose, but the final contour that you choose is something like this. It may do a very complicated thing in the inside, but its end should be fixed at plus minus I infinity.
I see. Okay.
Well, let us move to the next question by Anna Tokareva, because we are in need of shorter time. So Anna, please.
Follow up to the question by Luca. If we obtain exponentially growing amplitudes, then can't we conclude that we are in the strong coupling regime and our perturbation theory breaks at this point? So can it happen that resumming somehow in a non-perturbative regime, we can get smoothly going amplitudes at high energy?
Yes, the point in string theory, you don't encounter this problem, right? So that's why you don't worry about this, because the on-cell S matrix never grows. Right? As I described that in string theory, the on-cell amplitudes are actually good at high energy. They fall off at high energy. But if you have a generic non-local theory where the amplitudes grow, maybe one can do some resummation. I don't know but that can only be done in very specific theories. I doubt that a generic non-local theory will allow you to do such resummation. But in string theory, you don't really have to worry about this problem because you don't have growing amplitude. It's just the individual Feynman diagrams grow, but not the sum. Does that answer your question or not?
Okay, great. Actually, there are many questions, and I myself have as well, but I propose that we postpone next questions to the discussion, which will happen after all talks, because we must somehow follow the time. And now we're going to switch